Okay, so let's talk about making inferences for simple linear regression. So remember that under our model, we're sort of assuming that condition on the x variable value that the y values are actually normal random variables, and that they have common common error variance. Okay, so it's so there's a real sort of structure to these kinds of models, and making those assumptions, we can actually make hypothesis tests for the true correlation and the true slope, if we could find the true slope for the best fitting line running through the means of the y values, and the true y-intercept. Okay, so turns out that under those assumptions, the slope estimator B1 has a normal distribution with mean beta1. It's unbiased, that is. It's on the average, it is what it's supposed to be, and its variance turns out to be this stuff. Okay, and you can find the details of all that hammered out in your text. Applied linear statistical models. Therefore, if you take your best guess for B1, which is this, right? If you take what you actually get from your sample is B1, and then standardized it, according to its mean and variance, and well, you take the square root of the variance, right? That is, take what you actually get, your B1, subtract what it is on average, and then divide by its standard deviation, which is the square root of all of this stuff. That's how you standardize a variable, right? You take the thing, subtract its mean, divide by its standard deviation. Then what do you get? It turns out all of this stuff, you can work through the algebra there. It's just B1 minus beta1 here, all over sigma times the square root of all this stuff, right? Stuff in the denominator pops up. All of this, it turns out, behaves according to a standard normal. Okay. However, we don't know the value of sigma, so we estimate it with the square root of MSE, since it turns out that the mean square error is an unbiased estimator for the common error variance. So that's what we do. We fudge there, and we make that substitution, make that guess, and so it turns out that all of this stuff, which is the same as all of this stuff, just substituting in the square root of MSE for the sigma there, all of this stuff behaves like a t random variable with n minus 2 degrees of freedom. Hey, that's all we need in order to make confidence intervals and hypothesis tests for beta1. Okay, all you need to know to make an inference for a population parameter is, well, number one, you need a good point estimator for it. Number two, you need to know how that point estimator behaves. What's the distribution of that point estimator in theory. Then you can find your value of that point estimator, and you can do a hypothesis test, right? Right. So just a little note down here in the bottom. Note that recall that the slope of the regression line and the correlation are very related, right? In fact, B1 equals the correlation coefficient R times the standard deviation of the y values over the standard deviation of the x values, and that the B1 and R will have the same sign. Right? If the slope is going up, then R is going to be positive. If the slope is going down, then R is going to be negative. Similarly, beta1, the actual real life slope for if you could actually have the entire population and know exactly what the true regression line was. This and beta1 and rho, the correlation, are likewise related. Okay, so making inferences for one correspond to making inferences for the other. Okay, so we'll focus mainly on that. Is if beta1 equals 0, then when you're making a hypothesis test for beta1, that's the same as testing for, when you're testing, if your null hypothesis is that your slope is 0, it's the same as testing for the slope, for the correlation, the true correlation to be 0. Okay? So we will actually just focus our discussion on making inferences for beta 1 and beta naught, and a few other things, but not so much for the true correlation there. Okay, so what about beta naught? Well, it turns out that an unbiased estimator for beta naught is actually beta 0. Excuse that. And that the variance of B0 is all of this stuff. Okay, so yeah, so let's standardize B0. If I take what I get for my estimate for the y-intercept and subtract what it is on average and divide by its standard deviation, it's all of this stuff. Okay. Again, the details for all this are hammered out in your text, so I won't do them here. All of this behaves like a standard normal, it turns out, and again, we don't know sigma here, so we approximate it with the square root of MSE, because MSE by itself is an unbiased estimator for sigma squared. Okay, so it turns out then all of this stuff has a t distribution with n-2 degrees of freedom. And so again, so this is all we need to know to make confidence intervals and hypothesis tests for beta naught. It turns out all these procedures still work pretty well, even if the response variables aren't exactly normal. And even if they are far from normal, as long as the sample sizes are large, the distributions of B1 and B0 are approximately the same as they are above. Okay, so so these procedures are pretty good, especially if you have large sample sizes. So let's take a look at this used cars example. I promise we won't be on this used cars example forever, but probably throughout the rest of the chapter at least. So let's make 95% confidence intervals for the actual values of beta naught and beta 1, not simultaneously. We'll revisit this toward the end of this set of notes, but let's just make an individual 95% confidence interval for beta naught, and then another 95% confidence interval for beta 1. Okay, so also let's run a hypothesis test to see if there's statistical evidence to suggest that beta 1 is less than 0 and beta naught is not equal to 0. So we can sort of do this by hand, more or less. I've got R pulled up here. Again, I'm gonna get my age and price data in there, and I will I'll go ahead and calculate B1 and B naught. Okay, remember we have the formulas for those. B1 is R, which is the correlation between age and price, times the standard deviation of the price over the standard deviation of age. B naught is the average of the response variable values minus B1 times the average of the ages. Okay, and I can see what those are. There's my slope. There's my intercept. Okay, I can calculate the fits and the residuals. All right, if I do, so my fits, that'll be if I take my slope, multiply by age, and add all the values. You can see what's going on here. This age is really sort of a vector. I'm multiplying by the slope, each one of those values by the slope, and then adding. Now this is the way R works. It's not like this is not a vector here, but when it sees this, and this is an array, or this is effectively a vector, and then we're trying to add a constant to it here. It's going to add up. It's going to sort of you want to think of this now as a vector where all the values are B naught. Okay, so this will get the fits along the line. The residuals, of course, are the prices minus the fits, right? They're the errors there. I can take a look at those residuals if I like. Okay, I've got 10 of them, one for each data point. I can calculate SSE, my sum of squared errors, by summing the squared residuals. Okay, so SSE is right there. MSE is going to be SSE over its degrees of freedom, right, which would be 8. So MSE, there's my, and if I take the square root of MSE, then that will be my good estimate for the actual population standard deviation, so the standard deviation that for the errors, the common standard deviation for the errors. Okay, so now what I'm going to do is I'm going to do that long calculation for the standard deviation for the B1 there. Okay, so I'm just following the formula that's there in the notes. Standard deviation for B1. So all that stuff. I'll also go and get the standard deviation for B0. Just going to follow that formula. Okay. And hope you can see all that. You should check the formula in the notes. See that it's the same. Remember, the derivations of those formulas are in your textbook, so you can check that out if you want. I can see them here if I want to. There they are. Then to get a 95% confidence interval for beta1, I just let's see. I'll say my left and right endpoints will be these numbers, right? My left endpoint will be, again, this is an interval for beta1, so it's going to be my best guess for beta1 minus that t number times the standard deviation for B1, right? The t number, remember, we're making a 95% confidence interval, 95% confidence interval. So I've got to go to the 97.5, the 97.5 percentile, right? You might, if that's not clear to you, post a question about it in the discussion board. Okay, but and then I've got m-2 degrees of freedom there, right? Okay, and then the right endpoint is the same thing, but just plus all this stuff. Remember, all this stuff that you're adding or subtracting here, right in here, all of this is called the margin of error, right? And so I can see what that confidence interval is if I just do that. Okay, I can. What I would write in my report is that I can be 95% confident that the actual value for beta1 falls between these two numbers. Okay. Similarly, I can get a 95% confidence interval for beta0. I'm just copying and pasting from the notes here, by the way. Okay. Note that I've done exactly the same thing. Of course, like an idiot, I have overwritten my, the confidence interval points for beta1 here. I've sort of redefined them here, so they no longer exist. I'd have to redo them if I wanted them. Okay, so left endpoint for this new interval, it's my best guess for B0. Plus or minus the margin of error. Now the new margin of error, it's got the same t number in it, right? But it's got this. I'm using the standard deviation or standard error for B0. Okay. All right. So I could say that I'm about 95% confident that the actual intercept value for our model is somewhere between 170.8 and 227.24. Remember, these numbers will have units of $100 bills. Okay. Similarly, I can make a hypothesis test for beta1 being, say, like I don't know, less than -10. Okay. Here's a bunch of comment stuff. Remember, you can use the pound sign if you want to comment. If I want to run a hypothesis test, it says that beta1 is less than -10. Maybe that's of interest to you. Maybe if the slope is less than -10, meaning greater than 10 in magnitude, but going down, that means the depreciation is maybe it's higher than it has been or something. Okay, so what I want is I want to get a test statistic. Okay, so I'll compute that. Okay, here's my test statistic, beta1 minus, right, -10, and divide by its standard deviation. And then I can see what that test statistic is. Remember that this test statistic, you know, if under the null hypothesis adjusted, it should have a t-distribution. So this our p-value is going to be taken from a t-distribution with 8 degrees of freedom, right? And so our p-value is actually that, okay? So it's about 13–14%. So that's probably not sufficient evidence to reject the claim that it's greater than or equal to -10, okay? If the p-value had been really small, like 0.01 or something or less, then yeah, we could say that we're, you know, pretty confident that the prices are depreciating at a rate faster than 10 $100 bills per year or something like that. Okay. Or we might want to do a hypothesis test that beta1 just simply differs from 0. Now, right away, we already know that the p-value for this test ought to be pretty darn small because we've already seen the graph. We know that there's a high correlation. The points are, you know, riding right down along that line, and it certainly looks like the slope is I mean, seems to be a lot of visual evidence that the slope of the real line ought to be negative. So I can run that test too. And I'm just taking my best guess for B1, subtracting whatever the value is that's stated under the null hypothesis, 0 in this case. Last time it was -10, dividing by the standard deviation of B1. And so my p-value is then, since I'm doing a two-tailed test, okay, differs from 0. Since I'm doing a two-tailed test, it's 2 times that tail area, okay, from a t-distribution, pt, okay. This is the probability distribution for a t random variable. 8 degrees of freedom, and here's my p-value. Yeah, it's pretty small. So I would conclude that, yeah, it certainly seems to be a lot of evidence that it's actually different from 0. What if I want to test whether or not beta not differs from 0? Okay, well, so again, I have this word differs here, so that means we're going to do a two-tailed test. So I've got to find the tail area in both ends to get my p-value. So I get, since t distributions are symmetric, I just take 2 times the probability distribution there. I'm just, you know, so that I don't have to think about it, I'm taking the absolute value of this this test statistic here, and then finding the negative of it, so that I'm finding the mark down on the left side, on the negative side of the negative end of the t distribution, and finding the tail area out there, multiplying by 2, and get my p-value is pretty small. Yeah, so in fact it seems like our model is indicating that beta naught is that beta naught is not equal to 0, which makes sense because what is B naught? B naught should be indicating the price of a new car, right? Shouldn't be 0. It wouldn't make a whole lot of sense. Finally, what if I just type summary regression? Well, I don't have so finally, what if we do this? LM, let's see, we'll do, is it price versus age? Oops. Okay, and summary reg, see what happens there. Look at all the output that we get. Okay, it reminds us what we're doing here. Linear model, price versus age. These are some statistics on our residuals. Remember, which are the observed errors off the line. Okay, and here I get my regression coefficients. This is my intercept best guess, my B0. Here's my slope coefficient, negative 12.152. Standard errors for those, right? And here are my t values, and these are the p values that we got, but they are specific ones. They're for testing hypotheses about whether or not these the intercept and the slope equal 0 or not, whether or not they differ from 0. So in fact, you'll see these appearing up here. Like for B0, for the intercept, we got the p-value is 2.04924 times 10 to the negative 7th, right? They round to here 2.05 times 10 to the negative 7th. For the age, again, this is the output. The default output there is for test whether the betas are equal to 0. We got a p-value in that case of 0.00016 something. Okay, so that's what that is. So that's a heck of a lot quicker. You don't want to do it this long way. I like doing that just to make sure that I kind of know what's going on. But once you feel confident you know what's going on, then you can just do this.